This problem is taken and can be found from this website. And along with this example, there's also a lot of other great examples that you could look through in addition to your textbook. So we're going to go over an applied optimization problem. This problem begins by saying we've got a printer that needs to make a poster that will have a total area of 200 inches squared, and it will have margins that are 1 inch on the sides, 2 inches at the top, and a 1.5 inch margin at the bottom. And we're going to ask what dimensions would give the largest printed area. So by our printed area, we want to make this section as large as possible. And we'd want to do that within the constraint that the length and the width, whatever we call this would be, so this might be our length, and this is our width. We know that length times width would have to be 200 inches. So we would like to maximize this while keeping the constraint that the overall length times width would be 200 inches. The way we could think about maximizing this area is first to be able to express it. So notice that this length here could be seen as the original width minus 2 inches from either side. So if we're wanting to find the largest printed area, we're going to try to maximize the equation where we've got the width minus 2 inches times the maximized length here is going to be the length minus 1.5 inches from below and 2 inches from the top. And that'll give us the printed area. So what we're going to do is right now this is an equation in 2 variables. So we'd want to find a way to manipulate the constraint equation so that we could substitute that to get this area equation down to 1 in a single variable. So what we could do is maybe solve the equation for, let's just solve for length here. So we would get length is equal to 200 dividing both sides by w divided by width. And now we're going to substitute this expression for length, 200 divided by w, here into our area equation. This gives us the benefit that we now have an expression in a single variable. So width minus 2 times 200 divided by w minus 3.5, and that's our area expression. Now, if we simplify this by distributing, combining like terms if possible, then we'd be in a great place to take the derivative, because we know if we're looking for the largest area, this is an equation that has maxes and mins. So if we can find those maxes and mins, particularly the local max in this case, we would be able to answer the question of what would create the largest printed area. So distributing and combining like terms, we would get our area equation here. Okay, now if we take the derivative, we can look to find any critical points, and then we could identify those as local max, mins, or neither. So let's take the derivative. Taking the derivative, we would get a prime is 3.5 minus 400 times -1 w to the -2. We could simplify that. Now this function would have critical points either where a prime of w equals 0 or a prime of w does not exist. And in this case, the only value that would make a prime of w not exist would be when w equals 0, but based on the problem that doesn't make sense because that would mean the poster had 0 width, so this would not apply in this particular circumstance. So we would just need to set the equation equal to 0 and solve for w. Adding 3.5 to both sides, we would get this expression. We would then divide both sides by 400. Dividing by 400, we get this. Now we can rewrite w to the -2 as 1 over w squared, which we could simplify to get the expression. Then, if we take the square root of both sides, we would get w is equal to plus or minus the square root of 400 divided by 3.5. So algebraically, it would be both plus or minus, but in context, if we keep in mind the width represents the width of the paper, we know for our purposes, we're just considering the positive value, so that would be about 10.6904 inches when rounded. And this is going to be our critical point for the area function. We then need to determine whether this critical point represents a local max, local min, or neither. We can do that with a variety of methods, first derivative, second derivative test. I'll just go with the first derivative test. So we would begin to draw our number line, label our critical point. So picking a test point to represent all values before 10.6904, picking a test point to represent the values after 10.9604, and then just evaluating these in the derivative, we would get at the test point 9, the derivative is positive valued. At the test point 11, the derivative is negative valued. And that would just correspond to the idea that our area function is increasing for width values that are less than 10.6904. And then our area that we're printing would then start decreasing for all widths after that. Okay, so we've identified this critical point to be a local max. Since we were originally asked for the dimensions, we also want to find the length that would correspond to that, and we did have our original equation that related length and width. Originally, we knew that the length was related in that it was 200 divided by the width. Substituting this in and rounding, we would get about 18.7084 inches for the length. So these are going to be the dimensions that maximize area under the given constraints.